Just going to do one more example showing the method of initial rates. So you can just see some variety and some differences. So here, the problem says determine the rate law. You've got 3 experiments, you've got concentration, and it's give you the concentration of the reactants. We don't even know what the chemical reaction here is. It's not relevant. So what we're trying to figure out for A is the rate law. So in general, rate is going to be equal to some constant for that experiment at a certain set of temperatures. And then for this experiment, we've got this chlorine dioxide, and it's going to be raised to some power, which we have to determine. And then we have the hydroxide ion concentration, and it's going to be raised to some power. So A, we want to figure out what M and N are. B, we're going to then find the rate constant K, and then we're going to figure out what the rate would be at certain concentrations. So let's look at our experiments and the different concentrations. So from 1 to 2, we see a decrease in the concentration of the chlorine dioxide, and this one's staying the same. So we can use that to our advantage here to solve for what M would be. So let's do that. So I'm going to do experiment 1 over experiment 2 rates is going to be the change in the concentration of the chlorine dioxide raised to some power. So that's going to be, we've got the rate of experiment 1, 0.0248 mole change in concentration per unit time, molarity per second, over 0.00276 molarities per second. That's the rate of experiment 2, is going to be equal to the concentration of the chlorine dioxide and experiment 1 over what it is for experiment 2, raised to some power. And when you reduce this, these two divided, you're going to get 9, and then these two, you're going to get 3 raised to some power m. And so sometimes students, they just want to think about this. So 3 to the 0 power would be 1, and 3 to the first would be 3, and 3 to the second would be 9. It's usually a good way to do it if you're just trying to figure out what it would be. So that means that M is equal to 2. So as the concentration of the chlorine dioxide doubles, the rate quadruples. Cool. We haven't seen a second order. So it's second order respect to the chlorine dioxide. So that is what M is. Now we have to figure out what N is with the change in concentration of the hydroxide. So if we look at experiment 2 to 3, that's staying constant. And this one is the concentration, they're tripling it. Let's see what happens to the rate. So I'm just going to put experiment 2 over experiment 3. I'll put the smaller one just so you can see that it doesn't matter. You just have to think through it a little bit. So that's going to be the 0.00276 molarity per second over 0.00828 molarity per second is going to be 0.030 molar over 0.090 molar raised to some power n. When you divide these two, you're going to get 0.33, and these two, same thing, 0.33 raised to the n. So that means that n is equal to 1. So for A, then our rate law, the rate law for this equation is going to be rate equals K times the change in concentration of the chlorine dioxide squared and the change in concentration of the hydroxide to the first. So that's part A, the rate law. B, we want to determine the rate constant. So now that we have the magnitudes of how much each reactant affects the rate, we can determine the rate constant for this. You can choose any of the experiments. I'm just going to choose the first one. So I'm going to plug in the rate for that. So we're going to have 0.0248 molarity per second is equal to K. And then I'm going to do the concentrations at that experiment. So we're going to have 0.060 molar squared times 0.030 molar to the first. And when you do that, what you're going to have, write it over here, you're going to 0.0248 molarity per second is equal to K times 1.08 times 10 to the negative 4. And the units, it's molarity squared times molarity. So you're going to have actually molarity cubed. Okay. And so when you then move this term to the other side, so divide both sides by this, what you're going to end up having cubed is the molarity here is going to cancel, and this is going to become a square. And so K for this one unit wise is going to be numerically 230, but then you're really going to have, you can either write it as molarity to the negative 2 seconds to the negative 1, that's one way to write it, or you could write it as 230 over molarity squared times seconds, just so you see different ways. So that means that our rate constant, so the full rate law here, without putting in the numbers, would be 230. I'll put it molarity squared down here in seconds. And the chlorine dioxide squared and the hydroxide ion there. So that would be the full rate law with the rate constant solved. And then part C wants us to calculate the rate when you have these concentrations. So if we kind of plug those in, so part C, rate, and we can just, I want to show you the unit cancellation here. So 230 molarity squared times the seconds. And then we're going to plug in 0.100 molar, it's going to be squared, times 0.050 molar. And so you should see, so this would be, the 0.1 squared. So you have molarity squared times molarity. So your molarity cubed here, and you have molarity squared on the bottom. So again, rate should be molarity per time, or change in concentration per unit time, which we do get here because the two of these will go away from that, and you're just left with molarity to the first. And numerically, the rate for this one would be 0.115 molarity per second. So that is just another one more showing you what happens if you have a square there. And if you had a 0, then you just wouldn't include that one.